Okay, we've explored parametric equations a little bit. Now we're going to look at the calculus of these parametric equations. The first thing, of course, would be the first derivative. So for these parametric equations, we've got the x of t and the y of t. So we've got the horizontal description and the y description, or the vertical description. And what we're looking for is dy over dx. So the strange part about this is that our function is all a function of t. It's all in terms of t. Yet we're looking for dy over dx. So let's just break that down just a little bit. dy is asking for the change in y, and dx is looking for the change in x. So in this case, we're going to be more specific, and we're going to say change in y with respect to x, or with respect to time. Because it's just asking how is y changing. And so we're going to be more specific and say how is y changing with respect to t. And then similarly for dx, we're going to look for the change in x with respect to t. Okay, so let's take a look at that. For dy over dx then, dy, we're looking for how y is changing with respect to time. That's dy over dt. And for dx, that's dx over dt. And using the parametric equation that I defined above, x of t and y of t, dy over dt would be y prime of t, and dx over dt would just be x prime of t. Now just to algebraically show that this is the same, that dy over dt over dx over dt is the same as dy over dx, let's take a look at this. If we've got dy over dt divided by dx over dt. If I simplify this, I can flip that denominator and multiply. So I can flip the dx over dt. And I can see that the t parameters do cancel each other out, and indeed leaves me with dy over dx. Okay, so the first derivative is found by taking the derivative of the y parameter divided by the derivative of the x parameter. That's a mouthful. Let's go use this. So the first question is to find the critical numbers for this parametric equation. So the critical numbers are where the derivative is equal to 0 or undefined. So where dy over dx equals 0 or undefined. So why don't you go take a moment, see if you can find that derivative, and see if you can find the critical numbers as well. Okay, welcome back. Let's find dy over dx first. dy over dx is found by taking the derivative of y over the derivative of x. So in our case, with the parameters that were given to us, the derivative of y is 6t squared minus 6, and the derivative of x is 2t minus 4. Okay, we're looking for two things. We're looking where the derivative is equal to 0 and where the derivative is undefined. So when the derivative is equal to 0 is when y prime of t is equal to 0. So that happens when 6t squared minus 6 is equal to 0. If I factor this, I get two critical numbers. I get -1 and 1. If I'm looking where the derivative is undefined, that's when x prime of t is equal to 0. So that's when 2t minus 4 equals 0. And I just get one critical number from that, t is equal to 2. Now let's be more clear. Let's take a look at the domain restriction that was given to us. We're only concerned about the values between -2 and 3. Well, in this case, all of the critical numbers we found were in that domain, so those are all three critical numbers for this function, for this parametric equation. Now let's just say the question said, find the point on the parametric curve where the graph has critical numbers. This is just at what time does this happen? It's asking maybe where would the points be on the graph where this could happen. So what we would do is just take those values and substitute them into the parametric equation. I'll do one as an example. So for example, at t equals -1, if I wanted to find the point on the graph, I would just plug -1 into x of t. So this would be x of -1 So that's negative 1 squared minus 4 times negative 1. So 1 plus 4, that would be 5. And then also find y of negative 1. So that would be 2 times negative 1 cubed minus 6 times negative 1. So that's negative 2 plus 6. So I would have the point on the function itself at 5 comma 4. We have a critical number on the function itself. And you would do the same for t equals 1 and t equals 2 as well. Okay, so that's the first derivative and an application of it. So now let's go on. We're going to talk about finding the speed along a parametric curve. And I'm going to do more than that for this question. I'm going to do more than just finding the speed. I'm going to find velocity, position. I'm going to do it all so that you can see how many different applications we can do with these parametric curves. So let's just first take a look at the position. So this question says find the speed at t equals 1. So let's first find the position at t equals 1. We'll build our way up to the speed. So just bear with me. The position at t equals 1 is what we just did there at the end. We can just replace t with 1. So x of 1 is 1 squared minus 4 times 1. Y of 1 is 2 times 1 cubed minus 5 times 1. So the position at t equals 1 is negative 3 comma negative 3. Okay, useful but not super exciting. Let's go on and see if we can learn something else about this graph. Okay, let's find the velocity. Velocity is a little different in this case because we're looking at direction, we're looking at speed with magnitude in two different directions, horizontally and vertically. So the way we write a velocity for a parametric function is a little bit different than the way we would write velocity for any other function. So let's first find the velocity. We need to find the speed with direction. We need to find the velocity in the x direction. So I'm going to find x prime of t. That's 2t minus 4. And I'm going to find that velocity when t is 1. So 2 minus 4, that's negative 2. And I'm going to find y prime of t. So I'm going to find the velocity in the vertical direction, 6t squared minus 5. Y prime of 1 is 1. So when I write the velocity, I write it as a vector. And I'll show you the vector in just a moment. But when I write the velocity, it's called the velocity vector. So the velocity vector for this parametric equation is written like this with a pointy bracket, negative 2, comma 1. And we're saying that's the velocity vector, so everybody knows that this particle is at t equals 1. The particle is moving 2 units left and 1 unit up. We look at it as a vector, 2 units to the left and 1 unit up. That's the vector for velocity with parametric equations. Okay, we're going to go on now. Let's finally time to find the speed of this particle at t equals 1. Let me highlight my answer. Here's the velocity vector. Okay, now we're going to find the speed. The speed is how fast this object is going, but not the direction, because remember, speed is absolute value of velocity. Well, we have a velocity vector. So what we're trying to find out, we're not just going to take the absolute value of each one. The speed is, let me show you. If we've got this velocity vector, the speed is just how fast is it going from point A to point B. So it would be the magnitude of that vector. Let me show you what I mean by that. Since this is just a right triangle, this velocity triangle is a right triangle, to find that speed, I can just use the Pythagorean theorem. So to find the speed of this object at t equals 1, so finding the velocity was helpful because I knew the x, the horizontal magnitude, and the vertical magnitude. So to find the speed then, it would be the square root of 2 squared plus 1 squared, or the square root of 5. Let's see if we can write this more generically. So in this case, the speed at t equals 1 is the square root of 5. But let's write this more generically. The speed of any particle, of any parametric equation, speed of a parametric, I think that's of an object moving along a parametric equation is what I'm trying to say, would be this. It would be the square root of x prime of t squared plus y prime of t squared. So that's the speed of that particle. Okay, let's do one more thing in this video before I go on to the next one. The other thing I want to talk about is the second derivative, because in the next video we'll be talking about integration, so I wanted to complete derivatives here. Let's look at the second derivative. So we're talking about, let's just look at this like we looked at the first derivative. This is saying find the change in the first derivative. With respect to time. And this is saying find the change in x. And this is something we've done over and over and over for the entire year. The second derivative is, how is the first derivative changing as x is changing? The only thing we're adding on here is that this is with respect to time. So to write this in the more generic way, this is saying find this and find this. Let's be more specific. Let's clean this up a little bit. We already know what dy over dx is. So it would be the derivative of y prime of t over x prime of t. And then this would just be x prime of t. Be careful. This is not as straightforward as just finding a second derivative. We're finding the derivative of the derivative, as the numerator, over x prime of t, because we're saying how is the first derivative changing, and then how is as x is changing. Okay, so let's do an example. We're going to find the second derivative, and we're not going to do anything with it. We're just going to give it a try here. So why don't you take a moment, see if you can try this one and get as far as you can, and then we'll do it together. So go, try, and come back. All right, welcome back. Let's find dy over dx. So dy over dx is y prime of t, so that's 6t squared minus 6 over x prime of t. So that's 2t minus 4. There's the first derivative. But we're looking for the second derivative. So what we're looking for then is the derivative of this over the derivative of x. Be very careful here. The second derivative is different because we're looking at how is the first derivative changing as x is changing. Okay, so the numerator, we get to use the quotient rule. Notice I said get to. So we're going to use the quotient rule in the numerator. That would be 12t times the denominator without changing it minus 6t squared. So the numerator without changing times the derivative of the denominator, which is 2, all over the denominator squared. And then x prime of t would be 2t minus 4. We are going to take the time to simplify this because I think it's important for you to notice some things that are going on here. Simplifying is going to be important sometimes. So I'll distribute the 12t in here, and I'll distribute this negative and the 2 at the same time. All right, so looking at the numerator, I end up with 24t squared minus 48t. And then 2 times 6, that's 12, so it's minus 12t squared. 2 times negative 6 is negative 12, so when I distribute the negative, and then this is all over 2t minus 4 squared, and all of this is also over 2t minus 4. So I'm going to combine those 2t minus 4s to make this not a fraction with a fraction. So first of all, in the numerator, 24t squared minus 12t squared is 12t squared minus 48t plus 12. And then these 2t minus 4s will combine with that, so that's 2t minus 4 cubed. All right, there's the second derivative. Notice it was a little bit different than what we've been doing in the past. You really have to think about the fact that it's the derivative of the derivative and then over the derivative of x. Okay, that's it for this one. The next one we'll do some integration.